Hello, today we are looking at the focal length and lens power of lenses, and we're going to work out a formula, or we're going to use a formula to calculate the lens power, and we're going to look at factors that affect the focal length of lenses. Now, the first thing is, here we have a lens, so let's just remind ourselves of a couple of labels on here. This type of lens is called a convex lens or a converging lens, and the converging lens will focus light rays, as you can see here, on a particular point, and that point is called the principal focus. And another label you need to know is the distance between the lens and the principal focus, and you may remember that's called the focal length. And that's an important value that we need to know so that we can use it in our formula. And so getting to the formula, it's very simple. If you want to work out the power of a lens, it's just 1 divided by the focal length. So it's abbreviated to P equals 1 over F, and you'll be given this in the exam on the equations sheet. In actual fact, let me show you what it looks like on the equation sheet. It will look like this: P equals 1 over F, and it will tell you that P stands for power and F stands for the focal length, but it doesn't tell you the actual unit, so you must remember what the units are. For power, it's measured in diopters, spelt like that and shown with a capital D. And for focal length, very simple, it's a length, so we measure in meters and we use a small m. So how do we use the formula? Well, if we said we had a focal length of, I don't know, 0.5 meters for this lens, that's quite large, but let's just use that as an example anyway. Gives us a simple calculation. The power of the lens will be 1 divided by the focal length, which is 1 divided by 0.5, and that gives us an answer of 2. And remember, the unit is diopters. So this lens has a lens power of 2 diopters. Now we must remember that while that's quite straightforward here, for a convex lens sometimes we have a concave lens, and for a concave lens it's the same idea. We use 1 over F, but the value will always be negative. The value of lens power will be negative. So in this case, if we use the same focal length, it will be not 2 diopters, but it will be minus 2 diopters, simply because a concave lens requires a negative value for its lens power. So the next thing we're going to look at is this idea of focal length and factors that affect the focal length. So here we've got a simple diagram as we saw in the previous slide. Our principal focus there and our focal length we could put in if we wanted to, but something that will affect the focal length is the actual curvature of the lens, and the way the curvature of the lens can change is if we have a thicker lens. So this lens has 2 surfaces that have a different curvature to the first one. Curvature, and as a result we can see that the principal focus has now become shorter because we have more curvature on the lens, we have a thicker lens. So that's one factor that can affect the focal length. Second factor is the actual refractive index of the material that we use. So we've got the same lens as previous. This has a low refractive index. If we change the material of the lens, so we now made the lens out of a different material with a high refractive index, you can see again the focal length has changed. It's become shorter simply because we've used a material with a higher refractive index. The higher refractive index actually indicates that the light rays refract more. So the key thing to remember here is the focal length depends on 2 things. It depends on the refractive index of the material of the lens and the curvature of the surface. So refractive index and the curvature, and the curvature is usually related to the thickness of the lens, and that's quite important to remember. Now if you're doing the higher paper, it's also important for you to remember this: for a given focal length, the greater the refractive index, the flatter the lens. So let's keep the focal length the same as we have in this diagram here. If you look at the second diagram, we've got the exact same focal length, so that distance there is exactly the same, the focal length is the same, but we've got a material with a higher refractive index, and the consequence of that is that we can make the lens much thinner. Because this lens has a higher refractive index, it refracts the light more. We can maintain our focal length, keep the same focal length, but have a much thinner lens, and that is useful if you want to have glasses that are thinner, which means they're not so heavy and they probably look a bit better as well. So this is important for you to remember if you're doing the higher tier. The last thing, just quickly, I think we could possibly do is just try a couple of calculations for our lens power. This is very straightforward. We've got a lens here, a focal length of 0.2. So if you remember the formula, it was power is 1 over f. So in this case it'd be 1 over 0.2, and so the lens power here is 5 diopters. If we then took a second example, let's have a lens which has a focal length of 0.1. In this case it would be 1 over 0.1, and that would be 10 diopters. And if you think about it, that actually makes sense. This lens is actually refracting the light rays more. The principal focus is nearer, so we get more refraction, and it makes sense to think about and say actually and work out that the lens power is much greater, more refraction going on. And the last thing just quickly to remember is if we could swap this lens with a concave lens, and the only difference there would be, if you remember, is we'd have 1 over 0.1 again, but it would be minus 10 diopters. Okay, so that's an overview of the focal length, factors that affect the focal length, and the refractive index and how that links to different kinds of lenses. Thank you for watching, and I'll see you in the next video.